Hi, everyone. I'm Curt Frye. In this movie, I want to continue my discussion of the traveling salesman problem by showing you a way that creating what you think is a good constraint for a problem actually makes things a lot less efficient. The sample file that I'm using is TSP Effective Constraints, and you can download it using the link in the video description below. This is a traveling salesman problem like I've been creating throughout this playlist, so I won't go into a lot of detail on what's going on. Instead, I'm going to focus on the effective constraints that you think will help make a better workplace when they actually don't. So over on the left, I have my station list, 1 through 15. The drivers will be starting at station 15. Each of them can hit 7. And the distances are calculated over on the right in the distance matrix. I have a separate movie showing you exactly how to make those calculations. Below that, I have the stops for each of the drivers. Route 1 starts at 15, as does Route 2, and then we have 1 through 14, which are the stops they can stop at. And of course, the distances are calculated on the right. Below that, I have my total of miles that will be traveled. And then over on the left, I have a ratio, and this is the new constraint. So if I want to make sure that my drivers drive about the same distance to give them approximately equal amounts of work, then I have a ratio. So I currently have a ratio of 0.99, and if I click that cell, it is the minimum of the two distances divided by the maximum, and that ratio is currently 0.99. And I have the minimum ratio set to 0. Let me change that to 0.8 and enter. I currently have a valid solution, so instead of having all the values from B21 through C27 be actual station numbers, I'll just type 3 in B21, press Control Enter, and now I do not have a valid solution, so Excel will have to find one. I'll go to the Data tab, click Solver, and I have most of the solver model already created. I have the objective, which is the total miles minimum by changing the yellow cells, and then all of the cells from B21 through C27 must have the values from 1 to 14, and they must all be different. I also want to create a constraint so that the ratio that we calculate in B30 is at least 0.8, which is in B31. So I want to make sure that neither driver has to go 20% longer than the other in terms of miles traveled. So I'll go back to the parameters dialog, click Add, and the cell reference will be B30 must be greater than or equal to, because we're looking for equity, the constraint value, which is in B31. Now click OK. Everything looks good, so I'll click Solve and come back when Solver is done. Okay, we have our solution, so I'll click OK. And here we have a ratio of 0.84. The distances are 102 and 122, and the total miles is 224. So there's our solution. And if I look over, it appears that it's okay. We have one route in orange that looks fairly good, and the other one kind of goes out of its way a little bit. And one of the reasons is that we are forcing perhaps an inefficient route because we're trying to make equity based on mileage. So again, that distance or difference of only 16%. So now let's reset our variable cells to 3. And that could be any number, doesn't matter. I just want to move away from the existing solution. And then the ratio is currently 1, but let's set the minimum ratio to 0 and enter. So now we don't have a constraint effectively because every value will be greater than or equal to 0. So let's go back up to Solver and rerun the model and see what the optimal solution looks like. All right, we have a new solution, so I'll click OK. And this solution, just looking at it, seems to make a lot more sense. And if you compare it to what we had in other movies, the shape in general looks exactly like what we saw earlier. The criteria that we wanted for fairness or equity was approximately equal mileage. However, it took a lot more time for our drivers to do that. And in fact, we had at least 50 more miles that they had to travel. And the result of taking away the ratio criterion or constraint is that we have one route that is about half of the length of the other. So 61%, or rather 61 miles versus 113 miles. Because there is such a significant difference between these two routes, it's probably better to use something other than miles traveled as the basis for our fairness or equity toward our employees. One employee might have a preference of taking the shorter route and coming back to the office sooner in the day. The other might prefer to be gone longer. Or if they don't have a preference, then you could alternate them daily. So the main point is that you have some flexibility in finding routes that aren't as efficient if it's good for your employees. However, in a situation like this where the difference is so significant, it's probably better to find another way to be fair and meet your employees' needs than rely strictly on a numerical measure that you make efficient using a solver engine. I hope you enjoyed this discussion and demonstration of how to create this kind of model in Excel. If you did, please like the video and subscribe to my channel.